drug. We're talking about 47,000 drugs that might do any one of these things. So just take it for granted that this is the effect that it's going to have. And we know that if I say it's a physiologic antagonist, that it's going to do the opposite. Competitive is going to block it. Non-competitive is just going to slow it down a little bit. All right? Okay. We have to get the neurotransmitters of the drugs into the cells, okay? And remember, neurotransmitters are our body's own chemicals, our own drugs, if you will, okay? And there are different systems that are available to move the drugs into cells. There can be active transport pumps, which is just like it sounds, something that needs energy to get it going. And there are passive transport channels, okay, through the different membranes and cells of the body, okay? We're going to talk more about that in a bit. But they have to get to where they're going. So talking about where they're going, we're going to talk about pharmacokinetics, okay? This is going to involve this passage across body membranes. It's going to involve a number of different processes, and we're going to talk about like the ADME, right? You guys have read about that, the absorption, the distribution, the metabolism, and the excretion. The half-life of a drug, how long does it hang out in the body and exert its effects? We're going to talk about the difference of drugs getting through the blood-brain barrier, really important one. And we're going to talk about when drugs redistribute themselves to different parts of the body than where we want them to work. We'll talk about all of these individually. So the pharmacokinetics, or the PK, it's sometimes abbreviated as, I don't think your book says that, but I see that a lot, is the study about movement of drugs through the body. How does the drug enter the body, circulate within the body, it gets changed by the body, okay, it packages it up and leaves the body, right? Because we want it to get in, have its effect, change it up a little bit, and get it out, okay? Kinetics are movement, right? Kinesthetics is movement. So how does the drug move into the body, through the body, and out of the body? Remember the ADME, okay? It's a great way to remember this. It's a great mnemonic, okay? Like ADME to your body, okay? And then get rid of it. Absorption, distribution, metabolism, excretion. Okay, really good way to remember that process. So getting into the body involves going through cell membranes, okay? And that could be into the cell. Body membranes could be the cell. It could be into your capillaries, right? Into your blood system, and then into your veins and arteries and all of that. And it could be into the fluid, interstitial fluid between the cells. Okay, all of those different places. So we need to know a little bit about body membranes and how drugs are going to work in getting into and out of them, okay? So the membranes, no matter where it is, okay, on the different places within your body, and it could be one cell thick, it could be several cells thick, but they share characteristics with each other. All of our body membranes do. They're composed of lipids, proteins, and carbohydrates. Okay, so fats, proteins, and carbohydrates. Sounds like a diet, right? Okay, the balance between those two. That's why we eat these foods, because our body is made up of them. Okay, and water should be in there, right? All right, lipids are fats, proteins, and carbohydrates. Okay, the lipids. Okay, did you ever put like oil and vinegar together, and you can see how the oil and the water don't really mix together all that well unless you kind of emulsify it and whatnot? The lipids are basically impermeable, okay, to ions and polar molecules. So if you think about that, lipids like things to be quite neutral, okay, and not polar, positive or negative, and very neutral, okay, that's correct. That's correct. The membrane proteins you're going to see the proteins are on the membranes, and they help to move the drugs or the endogenous substances or whatever it might be, water, okay, through the membrane itself, okay, through the fabric of the membrane, through a transport process. There's several ways that they do that. And the carbohydrates combine with either the protein, lipids in their movement, okay, in their movement. So there's a certain way that these lipid molecules orient themselves to each other in the membrane. It's kind of cool. Again, it's kind of like a fabric, if you will. And you will notice that it almost looks like a little head with feet, okay, without arms there, if you will. And it's like, they call this a leaflet, okay? And the hydrophobic, okay, and if it's hydrophobic, does or doesn't like water?
Does not.
Does not, okay, hydrophobic. And if it's hydrophobic, it likes fats, so it's lipophilic, okay, means it likes the fats, okay? Are the ends, okay, they're in the middle there. And the hydrophilic, if you will, okay, or the little ends that are hydrophilic that like water are on the outside, okay? So it's impermeable. So the fat loving ones are in the middle, and the water loving ones are on the outside. There are little spaces in between them, and if a substance is very small and has low molecular weight, very little tiny particles, they can move through those spaces pretty easily. Okay, we know about osmosis, right? They can move through it very quickly, okay, and very easily. There's a great little video here that I have for you, and it looks just like that little thing that I showed you there. There's these little cute guys lined up there, all right? And it's going to show you the cell membrane structure and how things move across these body membranes, and how a drug might do that as well as our body processes. So here we go.
Between the living machinery of the inner cell and the harsh conditions of the outside world stands the cell's plasma membrane. As crucial as this barrier is, it's surprisingly flexible. Push it and watch it move. Poke hard enough and it might break and begin to regroup. The lipid molecules of the membrane naturally assemble in a double layer because their tails repel water as their heads attract it. Throw in some cholesterol and a few carbohydrates, and you have the basic structure of a plasma membrane. Within these lipid molecules, we also find different proteins which do various things for the cell. For instance, they receive signals from the world outside, or they transport nutrients and waste. So nature composes the membrane with a combination or mosaic of different lipids, carbohydrates, and proteins. And these molecules are not stationary. They constantly move within the structure, fluidly changing their positions. The survival of all life rests on this veil of material. A supple membrane just 2 molecules thick.
Okay, cool. So it helps to give us a mental picture about how things move in and out of cells and body membranes. What is that video called? The cell membrane structure. It's going to be posted. Okay. Yeah. And the link is right there. If you can either get to it through the link that I give you, or you can just put that into YouTube and find it. Okay. So remember, they can pass through. Passively. They can transfer through passively, or through specialized transport. There's different ways that they happen. What we know about substances that move through there, including drugs, is that the more lipid soluble, okay, the more they have an affinity for fats, lipid soluble substances, they move across that lipoprotein membrane, okay, more easily and through that simple diffusion. We know what diffusion is. So if we look at drug A, okay, D for drug A, okay, it moves very simply across there by passive diffusion. Drug B has a little positive charge on there, doesn't it? We'll talk about why that's not moving through very easily. Water-soluble molecules, okay, that are small enough, okay, so we talked about lipid-soluble. The small water-soluble molecules can pass through, okay, through pores if there's enough water behind it, okay? So with enough water force, they can pass through very easily. Now the specialized transport, certain substances have to get in there, and they go through some of the proteins that are in the cell. They might push themselves into the cell, and they can do so through a couple of different kinds of processes. Active transport, okay, and facilitated diffusion. And the active transport, we know that you've heard of the idea that something passes through across a concentration gradient. Does that sound familiar? That diffusion usually happens when you go from a high concentration to a low concentration. It just kind of diffuses over, okay? It becomes soluble and diffuses over there. But active transport, we sometimes need to transport a drug into something where we're going actually from an area of low concentration to an area of high concentration, okay? So against a concentration or even an electrochemical gradient, okay, against the way that nature would have it go, okay? And then facilitated diffusion happens through another process, for example, pinocytosis. This should sound familiar from some of your old biology, okay? So it doesn't move across the concentration gradient, okay? It moves into the cell in another way. It gets packaged up and pulled in. And guess what? I have another video that does that, because I don't think any amount of words I tell you, trying to get a mental picture, help as much as seeing it. And some brilliant people that can draw, you know, came up with these videos, and they're really, really helpful. Okay, so here we go with our active transport. My videos are working today. I am so happy. Okay, here we go. 6 minutes long. We might not play all of it.
The smallest unit of life is the cell. In order for life to be sustained, nutrients and gases must be able to pass into a cell. Wastes and other products must be able to pass out of the cell. Many of the materials that pass in or out of the cell do so by passive transport. In this process, there is no energy, no ATP expenditure by the cell. Concentration gradients allow for the movement of materials. Osmosis and dialysis, both specific types of passive transport, use this concentration gradient of high to low. Another type of passive transport is facilitated diffusion. Since it is passive, the high to low concentration gradient is present. However, the process is facilitated by a carrier protein. The carrier protein is somewhat like a revolving door, allowing easy access across the membrane and then rotating back to the other side. All of these processes, osmosis, dialysis, and facilitated diffusion, are passive. The cell does not have to use any energy to move materials by these methods. The concentration gradient is used. However, there are materials that need to be moved against their concentration gradient. This process requires energy, ATP, and protein carriers that are found in the plasma membrane. Defined active transport is material moved from a low concentration to a high concentration through a membrane using a protein carrier that requires ATP. An example of active transport is the mechanism of uptake of iodine by the thyroid gland. Iodine is essential for the manufacture of hormones that influence body metabolism. When you eat a meal containing iodine, the iodine will pass from the small intestine into the circulatory system. As the capillaries pass through the thyroid gland, iodine diffuses out of the circulatory system. Iodine attaches to protein carriers in the thyroid cell's plasma membrane. Being proteins, they have a unique shape, so only iodine will fit. Glucose, which is also actively transported into the cell, relies on a different protein receptor. The energy required is somewhat analogous to a rock being pushed uphill. The processes of simple diffusion, osmosis and dialysis, facilitated diffusion, and active transport allow for most all of the small material, those dissolved in plasma and extracellular fluid, to pass in or out of the cell. Large particles, however, pass into the cell by endocytosis. This is an active process. It needs ATP. In this process, the plasma membrane surrounds the particle, such as bacteria or a food morsel, and forms a vesicle that pinches off from the membrane. The cell does this in two different ways. One way is called phagocytosis. In this method of cell eating, large particles are surrounded when the cell extends the plasma membrane and engulfs the particle. The result is a membrane-bound package of material. Fluids that the cell wants to take in enter by a process called pinocytosis. In this type of endocytosis, the cell membrane sinks in, the material sinks inward, and the membrane pinches off. The cell uses energy for this movement. In both types of endocytosis, the cell ends up with a membrane-bound vesicle. The material in the vesicle still has to pass through the membrane in order to be used by the cell. In this case, the lysosome joins with the vesicle and digestive enzymes break down the material to particles small enough to pass through the membrane and into the cytosol.
Okay? That's helpful. helpful to remember. Again, a good mental picture for you as we talk about this stuff, okay? And again, those processes happen in everything from fighting infection to how drugs work. So it's just a general process. All right, so let's go through some of the ADMEs, some of the pharmacokinetics and how the drugs get into our body and get absorbed and work, okay? So absorption is the process by which the drug is transferred from the site of administration, okay, to the circulating blood, right? It has to get into our blood to work, okay? There are drugs that also have local effect, and getting into the blood actually gets rid of them. But in general, they need to get to where they need to go in order to work on the tissue they need to work through. Of course, this requires going through the biologic membranes, which we just talked about. And things that affect how they get in there have to do with some of the stuff we talked about already. The solubility, is it lipophilic and hydrophobic or fat soluble, or is it hydrophilic and water soluble, okay? We discussed how those might have an effect. The ionization of the drug might have an effect. Its pH, okay, may have an effect. So is it polar, okay, positive or negative? Is it an acid or is it a base, okay? We know acids have a lower pH, bases have a higher pH, somewhere along that scale, right? And when we talk about local anesthesia, it gets to be really, really important, okay? Factors that affect how it's absorbed is also the dose form, okay? Is it an oral absorption of a capsule, an oral absorption of a tablet, of a liquid, okay? And also, what about a parenterally administered or injected drug, okay? How is it absorbed from the injection site? So ionization, okay, and these are concepts, they take a little while to wash over you, okay? Drugs that are weak electrolytes, okay, positive or negative, disassociate or break apart in solution, okay, into a non-ionized and an ionized form, okay? They disassociate. The non-ionized, uncharged form is similar to those lipid-soluble compounds, okay? They readily cross body membranes. Non-ionized, uncharged, lipid-soluble, okay? Memorize those. The ones that are ionized do not cross over as readily. So the body likes uncharged fat. Okay, you will. Yes.
Is it still a part of absorption?
Yes. Yes. Okay. This is the effect of ionization on absorption. Okay. Crossing bodily membranes to be absorbed into the body to the site where we want them to work. Okay. The pH at the site where the drug is going, okay, and this dissociation characteristics we just talked about, okay, will determine the amount of drug that's in the ionized form and the unionized form, okay? Because the pH at the site where it's going may be basic or may be acidic, okay? And the proportion of the drug that's in that non-ionized, non-polar form, okay, is going to determine the ease at which the drug will penetrate the tissue and work. So, drugs are usually weak acids or weak bases, okay? If it's a weak acid, has a lower pH, right? The lower end of that scale there, right? Neutral being in the middle. If it's a weak acid, okay, and the site where you're injecting it into is basic or higher, okay, the ionized form increases and it's not absorbed as well. Does that make sense? Okay, it makes it harder to penetrate tissues. Say if you're injecting into an area which is basic and your drug is an acid. If the area is low, okay, or more acidic, the unionized form is going to increase and it's going to penetrate the tissues better. Nothing probably meets home about this better than when we talk about local anesthesia, okay? And you're gonna have this presented to you again, but it's really helpful to remember this. If the drug starts out as a base, it's a weak base, okay, and the site of absorption matches it and it's higher or basic, the amount of the non-ionized form increases, okay, the good stuff, making it easier to penetrate. If they match, There's more non-ionized, it penetrates, okay? Makes sense. If it's low, the opposite, the ionized form increases and we have poorer absorption. All right? So if they don't match, we have poorer absorption because there's more of the ionized form. All right, pretty simple. Layla, do you have a question?
Just trying to get so a drug would have the non-ionized and the ionized together in a drug. Let's
Right,
say
right. And they're gonna disassociate, right? Into ionized and non-ionized.
Okay.
So if we say inject them or take them into a site that matches their pH. So if it's a base to a base, there's gonna be more non-ionized, it's gonna get absorbed faster, okay? If it's an acid to a base, or a base to an acid, there's gonna be more of the ionized form and it's not gonna be able to be absorbed as easily.
So it would be like I'm walking into a spot and then there's more than what I like, then that part of me is gonna get, it's like the drug is gonna get more of, become more unionized and then go in. Is that what it is? That's the part that I'm not,
Yep.
because we have
If
both
it
of them.
matches,
If it
if the drug matches the site where it's going,
and enhance the.
it enhances its effect because it's gonna make it easier to be absorbed.
Okay.
And it has to be absorbed just to start. A is the beginning, right?
Yeah.
A is the beginning. Okay, so again, when we revisit this passage through the cell membrane, okay, we're looking at this here where the high concentration to low concentration happens because we got a drug which is unionized, okay? It has no charge on it and it's in that form. So it goes through. Now we have the drug here that's polar, that has a positive charge to it, okay? And it doesn't pass through. It doesn't pass through. Very, very simple. Okay, so here we go with a sample, an example here. Local anesthetics are weak bases. Okay, they are basic. When a body has infection in a local area, as it often does in the mouth, it makes the tissue more acidic. Okay, so the pH decreases. So when you inject a local anesthetic, which is basic, into tissue which is infected, it has less of an effect. So if somebody has an infection and you're treating that area, you sometimes have to use more local anesthetic. Okay, and anyone who's ever, worked in dentistry knows that this happens. It's something that happens. All right, so that's something you're going to be running into. You're going to think, okay, I did this on the other side where there was no infection. I used, half a cartridge of local anesthesia. She was numb. I was able to work. I went into this side, she has a fistula, she has this stuff going on, we really need to clean this area, but she's just telling me that she still feels it, okay? Because it's not gonna get absorbed into the place where it needs to go at that point, okay? So really important to remember. And yes, you're gonna be sticking a needle this long into somebody's mouth that way. That's actually a really good injection technique as well, into that area. All right? And again, we'll revisit the whole thing in the local anesthesia chapter. Okay. What about oral absorption? Lots of drugs are given orally, right? Drugs that are administered into the GI tract, okay, from a dose such as a tablet or a capsule or a liquid, okay? If they're a tablet or a capsule, they have to be broken up first, okay? So we know that to happen. And we modulate how they break up sometimes, where they break up. So we talked a little bit about last week about how you might take a pill that has a coating on it so it doesn't break up in your stomach, but it breaks up in your intestines to get absorbed so it doesn't upset your stomach, okay? So they do that on purpose. But in order to get to that form where the body can use it, they have to be broken down. So the coating or the shell is disrupted, okay, one way or another. If it's an enteric coated one, it's gonna go more slowly. The contents have to break apart. This makes sense if you've ever watched anything dissolve, like Alka-Seltzer, right, okay? It has to disperse or spread, and then it has to be dissolved in the GI fluid in order to be absorbed. Makes sense, right? And we use that effect. We know how they're going to approximately break up. And we also know that sometimes we're told to take something with or without food, and that's going to affect how quickly it works. Sometimes it won't keep it from working, but it might take longer. If you just had a full meal and you take a pill, it might take longer to work than if you took it on an empty stomach.